Hello again, this is James Camp from Lee College in Baytown, Texas, and this is my commentary on Chapter 10 of Big C++ by K. Horstmann. The topic today is object inheritance. In the last chapter, we talked about classes called taxi and car. Taxi and car are both vehicles, so that means they both inherit certain common characteristics from what we might call a vehicle class. Okay, they can both hold passengers and they can both go places. So those are properties of a vehicle, which taxi inherits that ability to hold passengers and go places, and so does car. But their implementation of vehicleness is different. You drive a car actively. You get in the front seat and you turn the steering wheel and push the pedals, while you get in the back seat of a taxi and just tell the taxi driver where to take you. So your interface, in other words, with a car is different than your interface with a taxi. So they both inherit certain characteristics from the superclass, the vehicle class, but they both change the implementation a bit. Also in the last chapter, one of your exercises was to write a class called circle and a class called square. We can think of circle and square as both being a type of shape. Okay, a shape would be a more general class. It still has a perimeter. Every shape has a perimeter and an area, but they're not very well defined for something that's just a shape. Okay, a circle and a square can inherit those properties from a shape and then define them. Okay, a circle would define area as pi r squared, whereas a square would define area as side squared. This is a very useful concept because we could have in our program an array of shapes, and one shape might be a circle and one shape might be a square, and another shape might be a right triangle, and another shape might be, I don't know, a hexagon. And each of those things would define their shape, their area and perimeter differently. And we could just call the area function and the perimeter function on each one, and that would do what we needed it to do. And that's the power of inheritance, and it's the power of something we call polymorphism, which is where if you have a superclass, a more general class like shape, if you have an array of shapes, each shape may be a different subclass of shape, and therefore we call that polymorphic, different shapes, literally. Okay, so this is how the UML class description system that we've been learning about draws inheritance hierarchies. There's an arrow with a triangular arrow points upward toward the more general class, and you can follow that arrow backwards to find the derived classes or subclasses. So vehicle is the superclass or parent class or base class of, for all different kinds of vehicles: motorcycles, cars, trucks. Motorcycle, we say, derives from vehicle, or we say it's subclasses vehicle, or we can call it a child class of vehicle. There are kind of competing nomenclatures for this. Okay, your book uses defines the relationship is that the more general class is called a base class, and the more specialized class is called a derived class. So shape would be a base class, and circle and square would be derived classes. Other terminology that you'll see in object-oriented literature for this is that shape would be a superclass, and circle and square would be subclasses. Another is that shape would be called a parent class, and circle and square would be called child classes. Okay. The derived class, the child class, the subclass inherits data and behavior from the base class. Okay. So every car is a vehicle, so it has wheels and it holds passengers and it goes places. Okay. Inheritance is often described as an is-a relationship, that whenever you have a more specific thing that you can say it is a more general thing, that's a situation where you could set up object inheritance. A square is a shape. A motorcycle is a vehicle. A car is a vehicle. A savings account is a bank account. A checking account is a bank account. So if you were setting up an object hierarchy for somebody's bank, you might have bank account as the base class and then have checking account and savings account as derived classes. Okay, some properties of this is a relationship. Okay, all cars are vehicles, so a car is a vehicle. All motorcycles are vehicles, as you can see from this diagram as well. All sedans are cars, but they are also vehicles. So you can say a sedan is a car, but because car inherits from vehicle, you can also say sedan is a vehicle. Vehicle is the base class for this whole object hierarchy. Car is a derived class from vehicle. Sedan is a derived class from car. Truck also derives from vehicle. Motorcycle also derives from vehicle. Okay. We define vehicle very generally because we know that everything about being a vehicle will be inherited by a motorcycle, a car, a truck, a sedan, and SUV. Okay. So vehicle in this case would just mean it has wheels and it holds passengers and maybe cargo and it goes places. Okay. Those things specific to cars, that they have usually 2 rows of seats so that there's a driver, a front passenger, and then rear seat passengers, though there are cars that don't have rear seats. It has a trunk and a engine compartment and some sort of cargo carrying area. Those things are specific to a car. Those things are inherited by sedans and SUVs. Sedans have front and rear seats and an engine compartment and a cargo compartment. So do SUVs. Motorcycles do not have all of those things. They have 2 wheels instead of 4 wheels. They don't have, the engine usually sits between the rider's legs, not in a compartment separately in the vehicle. If they have cargo compartments, they're not arranged the same way that they are in a car, a sedan, or an SUV. The substitution principle states that you can always use a derived class object when a base class object is expected, because the derived class object inherits all the properties and all the behaviors of the base class object. It may redefine some of those parameters and behaviors, but it has at least an equivalent of all those things. So if vehicle has a method, a member function, go somewhere, then a motorcycle inherits go somewhere, a vehicle inherits go somewhere, a delivery truck inherits go somewhere. So since a car is a vehicle, an algorithm that expects to take a vehicle object as a parameter and tell it to go somewhere can take a car as a parameter and tell it to go somewhere, and it will work correctly. Okay. Streams we've seen as a set of objects or a set of classes in C++ that are part of the standard library. They're how the standard library chooses to handle not only console input and output, but file input and output, and even building and taking apart strings. Okay. If you had a function process input that took an iStream as a parameter, you could call it with an IF stream instead, or with the CN object, or with a string and iString stream object. Why? Because each of those are subclasses of iStream. iStream is more general, so IF stream, iString stream, CN all have the same, all have inherited the member properties of iStream, and so process input will know how to interact with a CN, an IF stream, or an iString stream. Okay, this is the rather complicated inheritance diagram of the C++ string hierarchy. C++ has something that most other object-oriented systems do not have, called multiple inheritance, which means IOStream can actually be a child class of both iStream and OStream. It can do input and output, and that allows us to have one F stream. It allows us to have one F stream that does both input and output. But what I want you to see here, though, is that if we were looking at the iStream example in the previous slide, iString stream, IF stream, IO stream all inherit from iStream, and so they all can be used with that same member function. Another example of inheritance. Let's say you've designed an inheritance hierarchy for musical instruments. Guitar would be derived from instrument. Acoustic guitar would be derived from guitar, and electric guitar would be derived from guitar. You could pass any guitar object to a function tune that would then, prompt you, I guess, to tune each of the 6 strings on a guitar in turn. Which of the following objects could and which could not be passed to the function tune? Well, acoustic guitar derives from guitar, so my acoustic could be passed. Electric guitar derives from guitar, so my electric could be passed. My guitar is just a guitar, so of course it can be passed. My instrument, on the other hand, is a superclass of guitar. It will not have all of the properties that a guitar has, so the tune function wouldn't be able to work with it. So you couldn't pass a variable called myInstrument. Well, you could call it that. You couldn't pass an instrument type variable to the tune function as it's written here. Okay, we're going to be following through this presentation the example of making a quiz program. Quizzes consist of a series of questions. So question is a general class, a superclass. But there are different kinds of questions that each behave differently and have different member data, different properties. So a fill-in-the-blank question has simply a question and an answer. It might not need a derived class. All questions have a question and an answer. Choice questions, like choosing a single out of a list or choosing a multiple choice, those have to have not just the question and the answer, but they have to have a list of choices. So choice question would be a derived class that adds a property of having a list of questions. A numeric question that allows approximate answers might not have any different features than a fill-in-the-blank question in that it has a question and it takes an answer, but the method, the member function for deciding whether that answer is correct or not would be different, because instead of just checking does answer equal, does the answer the user provide equal the answer I have stored, the numeric question wants to allow maybe a decimal point difference here or there. Okay, so it has to judge the answer in a way that allows approximate answers. So here's how these could all form a hierarchy. We could have a question class, which simply has question text and an answer, and it has a method for supplying an answer by which it would, or supplying a user answer, and it would decide whether the answer is correct or not. Fill-in question, a fill-in-the-blank question, derives pretty simply from a regular old question. A choice question has to add data for storing the different choices. A numeric question has to change, revise, override the method for checking the answer. And then, you could further derive from choice question a multi-choice question, maybe one in which multiple answers are correct. Okay, so how would a question work? How would a question class hierarchy work? Well, any object of question should be able to set its question text and its correct answer. We're going to show this working the way that, a very simple way that the programmer writes hard codes the question text and the correct answer in the program. Ideally, we'd like a question object to read a question from a file and interpret the question text and the correct answer so that we could have multiple different quizzes that the same program could work with. But for this example, we're going to go with the simple way of having the whole question hard-coded in the program itself. When a user takes the test, okay, the program asks the question to display itself on the screen. So question1.display, and the question displays itself. The program then collects the user's response and passes it to the question object for evaluation. You would call question1.checkAnswer and pass the answer in the parentheses. And then the question would return a Boolean value, true if the answer is correct, false if it is incorrect. Now, every question, whether it's a multi-choice question or a numeric question or a fill-in-the-blank question, should have all three of these properties. So these properties would be, or behaviors rather, these three behaviors would be coded into the top level question base class or super class. But then we would have to create some derived classes. Choice would be a child class of question. ChoiceQuestion would need to also keep track of answer choices. So it's going to add data that stores its answer choices, and it's going to override, we call it, the display function. Okay, a choice question object will display its choices after the question text when question display is called. A numeric question needs to keep track of a range of acceptable answers. So maybe it's the answer for pi is 3.14 plus or minus 0.01. So you could put 3.13 or 3.15 and it would think that was fine. So it has to override the question : check answer function to check whether a number is in the allowed range. Okay, both of these changes can be done simply by inheriting and then altering or overriding is the word that's used in object-oriented programming. We override base class functions. The main program code then doesn't need to know what kind of question is being displayed or answered. It simply calls question display, it collects an answer, and then it calls question check answer. More on this in the next section. Okay, so how do we code all those different kinds of questions? Each of the different kinds of questions is a question object. Okay, so we start by coding the question base class, which will have a general function for setting the question text, a general function for setting the answer, and then a generalized function for displaying the question, and a generalized function for checking the answer, which would probably just say if student's answer equals answer, then return true. Each of the derived classes inherits the data members and member functions set up in ClassQuestion. Okay, then you add the unique features for each derived class. And the key here is that you don't have to rewrite the code that all questions have in common. You write the common code once in the question class, and then each derived class only has to write the code that's changed or that is unique to that question type. Here's the syntax for inheriting. We say class choice question, then we put a single colon, not the double colon operator, a single colon, and then we say public question. The keyword public there is important because it implies that everything that is public in the question class becomes public in ChoiceQuestion. Now, how is the choice question supposed to behave? It needs to display something like the following question. There's a question text, and then there are several answer choices numbered 1 through 4, and then the user would simply type 1, 2, 3, or 4 as the correct answer. ChoiceQuestion, therefore, has to have some sort of storage for the various choices for the answer. We would probably implement a vector of strings that would hold the answer choices. Okay. Question, however, the base class has only the question text and the correct answer, so we need to add that vector of answer choices. It needs a member function for defining answer choices, so we'll have to add that as well. And it needs a revised display function that shows answer choices in addition to the question text. The question class doesn't know how to display a multiple choice question because it only has question text, not answer choices. So in the ChoiceQuestion class, you'll have to rewrite the member function display. And as I've said a couple of times now, this is called overriding the parent class function. After specifying the class you're inheriting from, you only need to add the parts that are different. Okay, so the body of our class ChoiceQuestion would have, in the public section, we'd have a ChoiceQuestion constructor function. We would have an add choice function that adds a string as choice text and then specifies with a Boolean whether that choice is correct or not. And then we have display. We're going to override the display function from question, so we have to redeclare the display function here. Then in our private data, we would add a vector of strings called choices. Okay, the red box here shows how that would sort of be implemented in C++. The top half of the memory signature for ChoiceQuestion looks exactly like a question object. It's got text and it's got an answer. We then add under that any new data that has been added as part of our inheritance process. So choices is a new bit of data there. Okay, so the code on the left side of this screen shows the code that's inherited from ClassQuestion, the setText function, the setAnswer function, the checkAnswer function, and the display function. And then it shows the code for ChoiceQuestion that adds an add choice function and is going to override the display function. ChoiceQuestion inherits the private data text and answer from question, but it cannot access them because they are private and belong to the question class. Okay. The derived class inherits all the data members and the member functions that it doesn't override. So when we call ChoiceQuestion.setAnswer2, okay, that's going to call the member function of the base class and set the answer to 2. We couldn't call ChoiceQuestion.answer equals 2 because that's still private. An important point is that the choice question, the derived class, the child class, cannot directly access private data members from the base class or the parent class. Okay, just as you inherit certain things from your parents, but you can't go root around in their private drawers in their bedroom or something, ChoiceQuestion inherits those data from question, but it cannot access them because they are private. What it can do, as shown in this example, is it can call the setAnswer function from its parent class and pass it the number string that it's trying to set as the answer. Notice that you can call that without needing any kind of pointer to the parent class or anything, because you've inherited the setAnswer member function from the parent class. Okay, here's a silly example of a set of classes just for you to practice thinking about. Imagine that we have a simulation of a jungle, and the jungle is full of critters. Each critter has a history, which is simply a list of things that it has done in its life, and it has a position. You can get the history, you can add history to the history, you can get the position of the critter, and most importantly, you can call its own internal functions move and act. And the idea is that each critter knows how it moves in a particular way, how it acts when it's not moving. So you could define a class sloth that whenever you call the act function, it would add to its history the word eat or the word sleep, depending on which it had done last. It alternates between eating and sleeping. It would have to keep maybe a Boolean variable about whether the last thing it did was eat or sleep, so that it could keep adding that. You could create a derived class called nervous critter that during its act function, it shifts between position 0 and 1, okay, like shifting from one foot to the other or something. You could come up with many other critters that are perhaps more interesting to simulate than a sloth and a nervous critter. Okay. Common error in inheritance is leaving off the word public after the inheritance colon. If you leave that off, the default is for the inheritance to be private, and that means everything that was public in the question base class now becomes private in the ChoiceQuestion class, so that your main function could not call my ChoiceQuestion dot check answer, because that has been inherited as a private member. Okay, so the solution to that is to always use public inheritance unless you really mean to make everything from the base class private. Also, derived classes, as we've said before, cannot have direct access to private member data of the base class. So your ChoiceQuestion your ChoiceQuestion constructor function would have to call set answer, not text equals quest.text. Okay. Now, when some programmers encounter this kind of compiler error, they say, oh, well, I just need to add another variable called string text. This is a mistake because you're now overriding the base class's text, and you're not going to set the correct text. The base class, when you call display, is going to try to display its own text, not the derived class text, and so you end up having two redundant variables, one of which doesn't get used at all. The better way is to call the inherited set answer function and pass that along. Okay, one key point about inheritance. Inheritance is for when something has a different behavior or needs to track a different piece of data. It is not for something that just has a different type of value. So the example your book gives here is that if you wanted to track the fuel efficiency of cars, should you have a conventional car class and a hybrid car derived class? In this case, no. The only difference between the hybrid and the regular car is that the hybrid just has a better miles per gallon rating, but a single car class would be just as good at tracking the lower number MPG for a conventional vehicle and the higher number MPG for a hybrid. The behavior, you pull into a gas station, you fill up the car, and you record how many miles it's been since the last fill up, doesn't change whether you're a conventional car or a hybrid car. Now, however, where you would need to create subclasses is if one of your cars is a Toyota and the other one is a Tesla. Okay, you would need a gas-powered car subclass and an electric car subclass, because gas-powered car keeps track of how many gallons you put in the tank and determines miles per gallon from that. Electric car maybe keeps track of how long it's spent on the charger, or how many times you've charged it, or how many kilowatt hours it's stored in its battery, or I don't think it's been entirely defined how we track efficiency for electric cars. Some people do it per charging session, and some people do it per kilowatt hour and whatnot. But whatever you decide to track, it would be a different data field. You wouldn't be tracking gallons of gas, you'd be tracking charge. So the data field you're tracking and also the way you track it are now different, because an electric car maybe gets plugged in at home every night and fills up with charge, whereas a gas-powered car goes for maybe a couple of days and then you stop at a gas station and fill it up. So each of those things have a different behavior and they have different data that they have to store, so the implementation has to be different. And that's the key, the point that we're trying to make with this slide here, is that if the implementation has to be different, that's when you create separate subclasses. If the implementation is the same, but you just have different categories of data, you can have a flag in your car class that decides whether it's, Boolean is hybrid, okay? And you don't have to then subclass it into two different cars, because the behavior and the data that they're tracking is the same. Okay. Constructors. How do we construct derived classes? A derived class constructor can only initialize its own data members, because, as we keep saying, the base class data members are still privately held by the base class, but they still need to be initialized. The solution here is to use the same kind of initializer list that we had used when we had member data that were themselves classes. We did that last time. in this case, we're calling not member classes, but we're calling the base class in our initializer list. So your choice question, choice question, your basic constructor here maybe takes a question text, but then it has to pass that to the question base class constructor by using a question text. Okay. This syntax is admittedly somewhat confusing, but you'll get used to it eventually if you do enough of this. One other note is that when you do this initializer list, the base class constructor gets called before any of the code inside the curly brackets. So if that matters to you, most of the time it doesn't matter, but it's worth knowing. Okay. Now we're going to override some member functions. This is where our code gets exciting. Okay. ChoiceQuestion, you remember, needs to override the display method from the base class. It needs to both display the question text and display the answer choices. Now, good programming practice is to break this down into two problems. One, display the question text. Two, display the answer choices. We're going to tackle them in the opposite order. Okay, so a good way to start this is to write comments in your display function that say display the question text and then display the answer choices. Then we expand that second comment by saying, well, we just make a for loop that steps through the choices array and prints out the number of the choice, colon, and then the choice text. Note that we couldn't use the shortcut for loop that just says, for choice, colon, choices or something like that, because we need to know which number we're on. So we have to use the full old-fashioned for loop to do this. Okay, the first part seems easy too. You could just call the display function from the base class. Display, that's going to call questions display function. No, it's not. Okay, this is going to create a situation in programming we call recursion, where you're simply calling the same function over and over again, because it's going to, the compiler is going to interpret display as having this pointer in front of it. It's going to try to call the same display function that you're already writing right now. What you do instead, if you want to call the base class, is you give the base class name and then the scope operator, the double colon, and then the function. Okay. Note that an override function does not have to call the base class function, but sometimes it is expedient to do so. Common error, don't forget to use that base class colon member function notation when you want to call one of the member functions of the base class. Okay. Otherwise, again, you call the derived class function and you just call it recursively and nothing gets done. So here's an example of a program that uses ChoiceQuestion. We have question Q1. We set the text, we set the answer. We call Q1.display. We prompt for the answer, we get the response, we check the answer. Everything's great. We now have ChoiceQuestion Q2. We set the text, we add 4 answer choices, and we tell it that Denmark is the true answer to which country was Bjorn Storstrup born in. And then we call its display function. We get the person's answer, we check it, and the program is over. And this is what that program's output would look like. Who was the inventor of C++? Your answer, Bjorn Storstrup. True. In which country was the inventor of C++ born? Your answer, 2. True. Okay. We passed. Yay. However, there's a better way to do this than simply declaring a new variable every time you want to use an object, and that's to declare an array of objects, an array or a vector or whatever. In this case, we need to take advantage of what's called polymorphism, which is where the base class can stand in for many different examples of its derived classes. So you can have a single array of question, and it can have different question types as parts of that array. But there's some trickiness about how C++ implements this that we need to explore. In the main function of that last program, okay, we had to declare each question independently, Q1, Q2. What if we have a lot of questions? What if we're reading from a file and we don't know how many questions there are until we do it? It would be nicer if all the questions were collected in a single array, okay? Though some are base questions and some are choice questions. You could then loop through to present them to the user, and it would look something like this, okay? You have quiz, which contains, in this case, 2 items. You set the text and answer for quiz at 0. You can't do that with the choice question because quiz at 0 still thinks it's a question, not a choice question. So you create a new variable CQ, set the text, add the choice, and then quiz at 1 equals CQ. Then you loop through, call the display, take the answer, call check answer, and guess what? It doesn't work. Okay, it'll say in which country was the inventor of C++ born. It will not display the choices. This is because, as we talked about earlier, ChoiceQuestion, a derived class, its representation in memory is the top part of the memory looks exactly like a question, and then the inherited part is up at the top, and then any additions and overrides are implemented kind of in the memory after that. But when you assign ChoiceQuestion to a question type variable, it gets sliced off at that part where the new data is added, and only the old parts, only the inherited parts get copied over into the question object. In other words, a question object knows that it can hold a choice question object, but it will only hold the stuff that was derived, that was inherited. It won't hold any of the new stuff. So the solution to use objects from different classes in a single array is to make the array of pointers to objects instead of an array of actual objects in memory. Okay, that way no slicing occurs. You just have a pointer to each different object. Okay, and here's the key point of what enables polymorphism in C++ is that pointers to a base class can actually also be pointers to any object publicly derived from that base class. Okay, as far down the inheritance chain as you want to go. So a vehicle pointer can hold a motorcycle object, or a pointer to a motorcycle object, a sedan object, a SUV object, or a delivery truck object, as we go back to the beginning of this lecture. The opposite doesn't work. If you have a delivery truck object, it can't hold a pointer to a vehicle. That will generate a compiler error. So you can make your pointers at the top of the class hierarchy and contain everything below it, but you can't go the other direction. Another way of putting that is if you had a vector of question star, okay, that can hold pointers to anything that's derived from question star. If you had a vector of shape star, again, going back to the beginning of this lecture, it could contain pointers to circle or pointers to square. Okay, or you could create an array as question star quiz bracket 2. Okay, So let's try this version. Question star quiz 2. Quiz 0 is new question. Notice that we have to use the new operator because otherwise the pointer isn't pointing to anything. Quiz at 0, arrow set text. Quiz at 0, arrow set answer. Great. Now we can't create a new question for quiz at 1 because we want it to be a choice question. So we just create a pointer for that. We call it CQ pointer. Okay. We call the new choice question because otherwise it wouldn't be pointing at anything. And then we call set text and we call add choice. Now, if we wanted to call a constructor other than the default constructor, what we would do is we'd say new question, open parentheses, and the question text and close parentheses. Or if I'm setting up a circle, I'd say new circle, open parentheses, and maybe the diameter of the circle or something like that. Then we can set quiz at 1 equals CQ pointer, and because a higher, more general pointer can point to a more specific derived class pointer, that works. So we now have pointers in the quiz array. One of them's pointing to a question base class object. One of them's pointing to a choice question derived class object. And we're all happy so far. Now we call this code to display the quiz question, get your answer, and then call the quiz object to check the answer. And it still doesn't work. Okay. For reasons of efficiency, the call quiz at I display is going to call the question base class display function because the type of our pointer is question star. Okay. In C++, this is not the same. This does not work the same way in every other language, but in C++, the way you do this is that if you want the compiler to not always pick the base class function, you have to use the virtual reserved word. Okay, so any function, any member function that you expect to be overridden in a child class, in a derived class, you precede with the word virtual. Okay. All functions with that same name and parameter types in the derived class are then automatically also virtual. It's not necessary, but it's good practice to write the virtual reserved word in the derived class functions also, just to remind yourself that they are also virtual functions. Okay, you don't write virtual in the function definition, okay, only in the class header statement. When a virtual function is called, the compiled code is going to determine what type the pointer is pointing to at runtime, and the most appropriate override function is called. Okay, so quiz at I arrow display, it's going to check whether quiz at I is pointing to a question or a choice question, and it's going to call the appropriate function, which is what we want it to do. Okay, so the quiz vector is now set up to collect a mixture of all kinds of questions. Okay, such a collection is called polymorphic. Objects in a polymorphic collection are all have some stuff in common. They all inherit from the same base type, but they're not necessarily the same final type. Some of them may be base type questions, some may be derived type choice questions or numeric questions or something else. Each object knows on its own how to carry out its own specific version of these general tasks. It knows how it wants to display its question. It knows how it wants to check its response. Because of this, you don't have to define any, it cuts a lot of like if then statements out of your code, if else and such. You don't have to say, if I'm a numeric question, do this, or if I'm a choice question, do this, because the numeric question version of the function is only going to get called if it's a numeric function, if it's a numeric question. Okay, so now that we want to have a new kind of question called numeric question, it's going to override the check answer function. Okay, then we can populate any quiz vector with a mixture of plain questions, choice questions, and numeric questions. As long as a numeric question is a question, that works. Okay, so here's our complete program showing the polymorphism. Class question is going to have its own constructor, a set text, a set answer. It's going to have a virtual check answer so that that can be overridden. It's going to have a virtual display so that that can be overridden. And its private data is just going to be a text and an answer. Choice question is going to have a add choice function that adds a choice and sets whether it's correct. And it's going to have a virtual void display that overrides the display function. And it's going to add private data, a string of choices. Okay, they chose not to show us the text for the declaration for the numeric question because they're not using it in this particular program. We have a quiz array that contains 2 questions. The quiz at 0 is going to be a base class question, so we don't have to do anything fancy. The next question is going to be a choice question, so we set up a choice question pointer, set the text, add the choices. Quiz at 1 now points to the choice question. Then we check answers for all the questions. For I equals 0, I less than quizzes I plus plus. Quiz at I arrow display, get the user's answer. Quiz at I arrow check answer. We'll call the appropriate display and check answer functions for that derived class, or for the base class if that's what it is. Okay. Now some programmers feel like they need each derived type to know what kind of type it is, and so they'll add a string tag to indicate its class. So its type is question, or its type is choice question. You really don't need to do that if you implement your class hierarchy correctly, because if it's a numeric question and you're calling the overrided function, you're only going to get there if it's a numeric question. You don't have to then check whether it's a numeric question again. Okay. Remember, avoid slicing. Don't copy a derived class object into a base class variable. Use pointers. That will enable polymorphism to work correctly. One way to avoid this is if you have a function that takes a base class parameter, make it a reference parameter, not a copied value parameter. The copying of the value will slice off the derived class information. The sending of the reference will not. Okay. Finally, 2 functions can have the same name provided they differ in their parameter types. That's overloading. We've talked about that last time. If you have virtual void display and virtual void display with an O stream, those 2 can exist simultaneously. That's not an override. What happened here? Somebody forgot to add the keyword const at the end of the void display, and because that has a different implicit parameter, it's a question and not a const question, that doesn't override, it just adds another version of display. Starting with C++11, there's a new keyword called override that we can add to any function that's supposed to override its base class counterpart. You should use this, okay? So if void display is intending to override the base class, we just add the keyword override, and then assuming it's written exactly the same as the base class function, this will compile fine. If there's any error in the overriding, the compiler will generate an error, and you'll realize that, oh, I forgot a const, or I forgot a virtual, or something like that. Okay. When you work with classes, okay, some of which are general and others are more specialized, you'll need to build your own inheritance hierarchy. The first step is to list the classes that are going to be part of the hierarchy. I've got shape, I've got circle, I've got square, I've got triangle. Organize those classes into an inheritance hierarchy. Well, shape is at the top, it's the most general. Square, circle, and triangle should all derive from shape. Determine the common responsibilities. They're all going to have a size parameter, they're all going to have a area, and they're all going to have a get area function, and they're all going to have a get perimeter function. Decide which functions are overridden in the derived classes. Well, circle, square, and triangle are all going to override get area and get perimeter because shape doesn't define get area or get perimeter. Well, those are just empty functions for shape. Define the public interface of each derived class. Is there anything different about the derived class from the superclass, the base class? Identify any new data members that you need to add to the derived classes. Implement the constructors and write the member functions, and then allocate objects using pointers and process them. There's an example of this process in the textbook for a bank account class hierarchy. I've just given you an example for the shape, square, circle hierarchy. There are many other examples out there that we could talk about, but we're about out of time for this lecture. So now is a good time to work on the inheritance and polymorphism assignments for this week. Good luck, happy programming, and I'll be back later.